10,000 hidden planets were found in NASA telescope data. Somewhere inside NASA's telescope archives, buried beneath millions of measurements of starlight, scientists may have found one of the largest hidden collections of worlds ever detected. Not confirmed planets yet, but planet candidates. More than 11,000 possible planets, including over 10,000 that appear to be new. For years, NASA's TESS space telescope has been watching the sky, searching for tiny dips in the brightness of distant stars. Those dips may look small, almost meaningless, but they can reveal something extraordinary. A planet passing in front of its star, a shadow crossing light years of space, a hidden world announcing itself, not by glowing, but by briefly blocking the glow of its sun. And now, after a massive new search through old TESS data, astronomers believe thousands of possible planets may have been hiding in plain sight. The discovery is not just about finding new worlds, it is about a new way of doing astronomy. Because the next great discovery in space may not come from a new rocket launch. It may already be sitting inside data we collected years ago. To understand why this matters, we have to understand how difficult it is to find planets beyond our solar system. Stars are huge, bright, and visible across enormous distances. Planets are smaller, darker, and usually lost in the glare of their stars. Trying to see a planet beside a distant star is like trying to spot a tiny insect flying next to a lighthouse from thousands of miles away. So, astronomers often do not look for the planet directly. They look for its effect. One of the most powerful methods is called the transit method. Imagine a star shining steadily in space. If a planet passes between that star and our telescope, the planet blocks a tiny fraction of the star's light. For a short time, the star appears slightly dimmer. Then the planet moves away, and the star brightens again. If this dip happens again and again at regular intervals, scientists may be seeing a planet in orbit. The depth of the dip can help reveal the planet's size. The timing can reveal how long it takes to orbit its star. The shape of the signal can help scientists decide whether it looks like a real planet or something else. This is what NASA's TESS telescope was built to find. TESS stands for Transiting Exoplanet Survey Satellite. Launched in 2018, it was designed to scan huge areas of the sky and search for planets around nearby stars. But TESS does not simply take beautiful pictures of space. It measures brightness again and again, star after star, sector after sector. These brightness measurements create what astronomers call light curves. A light curve is a record of how a star's brightness changes over time. At first, it may look like a simple line, but inside that line can be noise, stellar activity, instrument effects, nearby stars, cosmic rays, and tiny signals from planets. Finding planets in this data is not easy. A planet's transit may block less than 1% of a star's light, sometimes far less. The signal can be buried under natural flickering from the star or artificial patterns caused by the telescope itself. This is why old telescope data can still hold new discoveries. The data may already exist, but scientists need better tools to read it. That is where this new search becomes important. Researchers analyzed more than 83 million TESS light curves from the telescope's first observing cycle. These came from full-frame images, which capture large regions of the sky and contain far more stars than the smaller list of specially selected targets. Many earlier searches focused on brighter stars because they are easier to study, but this new effort went deeper, examining fainter stars that may have been overlooked. Fainter stars are harder. Their signals are weaker. Their light curves are noisier. Their planet candidates are more difficult to confirm. But the galaxy is filled with faint stars, and if planets are common, then many of those stars should have planets too. After correcting the data and searching for transit-like signals, the researchers reported 11,554 planet candidates. Of these, 10,091 appear to be new. That number is enormous, but it must be understood carefully. These are not all confirmed planets, they are candidates. A candidate is a signal that looks like it could be caused by a planet, but still needs follow-up observations before scientists can be sure. This distinction matters. Science is careful because the universe can trick us. An eclipsing binary star can imitate a planet. That happens when two stars orbit each other and one passes in front of the other, causing a dip in light. A background star can blend into the same measurement and create a false signal. A star's own activity, such as spots or flares, can create patterns that confuse the data. Even the telescope itself can introduce small effects that look suspicious. So astronomers do not simply see a dip and declare a new planet. They test it. They compare it. They model it. They look again. One powerful follow-up method is radial velocity. When a planet orbits a star, its gravity pulls on the star. The star does not stay perfectly still. It wobbles slightly as the planet moves around it. That wobble changes the star's light. When the star moves toward us, its light shifts slightly blue. When it moves away, its light shifts slightly red. By measuring that shift, scientists can confirm that something with mass is orbiting the star. In this new study, one candidate was confirmed as a hot Jupiter. A hot Jupiter is a giant gas planet like Jupiter, but orbiting extremely close to its star. Instead of taking years to complete one orbit, it may circle its star in only a few days. These planets are strange because our solar system does not have anything like them. Jupiter is far from the Sun. Hot Jupiters are dangerously close to their stars, heated to extreme temperatures. Their existence forced astronomers to rethink how planets form and move. The confirmation of one hot Jupiter does not prove that all the other candidates are real, but it shows that the search method can find genuine planets, and that makes the larger catalog extremely valuable. Because even if only part of the list becomes confirmed, it could still add a major new population of planets for scientists to study. This is why the discovery is so exciting. Not because 10,000 confirmed planets suddenly appeared overnight, but because more than 10,000 possible worlds may have been hiding in data we already had. That changes the story. The telescope did not need to discover them again. Scientists needed to look differently. This is one of the most important shifts in modern astronomy. Today, telescopes do more than observe. They create archives. Every image, every measurement, every light curve becomes part of a massive scientific record. And that record can be searched again years later with better software, better computing power, and better ideas. The universe and the data does not change. Our ability to understand it changes. A signal that once looked like noise can become a planet candidate. A faint dip that was missed before can become a target for follow-up. A light curve buried among millions can become evidence for a hidden world. This is the new frontier of discovery. Not just bigger telescopes, smarter searches, better algorithms, deeper analysis, and a willingness to return to old data with new questions. The TESS discovery also reminds us that exoplanet science is still young. For most of human history, the only known planets were the ones in our own solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Then astronomers began finding planets around other stars, and everything changed. We discovered giant planets orbiting extremely close to their stars, rocky planets larger than Earth, mini-Neptunes, a type of planet not found in our solar system, planets orbiting two stars, planets with extreme heat, planets losing their atmospheres into space, planets in systems so compact that multiple worlds orbit closer to their star than Mercury orbits the Sun. Our solar system once seemed like the standard model. Now it looks like just one possibility among many. The more planets we find, the more creative the universe appears. That is why a catalog of thousands of new candidates matters. Large numbers allow scientists to ask larger questions. How common are planets around faint stars? How often do stars have close-in worlds? Are small planets more common than giant planets? Do different types of stars produce different kinds of planetary systems? How many planets have we missed simply because they orbit stars that were too faint or too noisy for earlier searches? A single planet can be fascinating. Thousands of candidates can reveal patterns, and patterns are how science begins to understand the galaxy. But there is another important point. TESS is especially good at finding planets that orbit close to their stars. That is because it watches each region of the sky for a limited time. If a planet takes years to orbit, like Earth does, TESS may see only one transit, or none at all. But if a planet orbits every few days, TESS has a much better chance of seeing repeated dips. So these candidates are not necessarily Earth-like worlds. Many may be hot planets, warm planets, or close-orbiting worlds. Some may be giant planets, some may be smaller planets, some may be false positives, and some may become some of the most interesting future discoveries in exoplanet science. This is how astronomy works. First comes the signal, then the candidate, then the follow-up. Then, if the evidence is strong enough, confirmation. The process can take months or years. Some candidates will be rejected. That is not a failure. It is the system working. Science becomes reliable by testing exciting ideas against evidence, and the evidence must be strong. Still, the possibility is breathtaking. Imagine thousands of worlds hidden inside tiny changes in starlight, each one orbiting a distant sun, each one with its own size, temperature, orbit, and history. Some may be blasted by radiation. Some may be gas giants wrapped in thick atmospheres. Some may be rocky. Some may be unlike anything in our solar system. Most will never be visited. Many may never be directly photographed, but their shadows can still reach us. A planet does not need to shine to be discovered. Sometimes it only needs to pass in front of a star. That is what makes the transit method so powerful. It turns absence into evidence. A tiny loss of light becomes a clue. A shadow becomes a world. And when millions of stars are measured carefully enough, the galaxy begins to look very different. Not empty, not rare, but crowded with planets. This has deep meaning for one of humanity's oldest questions. Are we alone? This discovery does not answer that question. It does not prove alien life exists. It does not reveal another Earth, but it expands the search. Before we can search for life, we need to know where the planets are. Every new candidate is a possible target. Every confirmed planet is a new laboratory. Every catalog helps scientists decide where future telescopes should look. The search for life begins with the search for worlds. And the more worlds we find, the harder it becomes to believe that Earth is the only interesting planet in the galaxy. Somewhere in these catalogs may be planets with atmospheres. Some may have water. Some may have chemistry that surprises us. Some may be completely hostile. But every one teaches us something about how planets form, evolve, and survive. That is the real power of this discovery. It does not just add numbers, it opens doors. It shows that even after years of study, NASA's data can still contain hidden treasures. It shows that our view of the galaxy is incomplete, and it shows that astronomy is becoming a science of both observation and rediscovery. We look outward into space, but we also look inward into the archives. The next major breakthrough may be hiding in a dataset already downloaded, a signal already recorded, a star already measured, a shadow already seen, but not yet understood. That is both humbling and exciting, because it means the universe may be revealing itself faster than we can interpret it. The planets are there, the light is there, the evidence is there, but it takes time, technology, and patience to recognize what we are seeing. More than 10,000 new planet candidates hidden in TESS data is not just a headline. It is a reminder that discovery does not always arrive with a dramatic image. Sometimes it arrives as a small dip on a graph, a quiet signal, a repeating pattern, a shadow crossing a distant star. And behind that shadow may be an entire world. A world with storms, a world with heat, a world with clouds, a world with an orbit, a history, and a place in the galaxy. We may never stand on these planets. We may never see their surfaces. But by studying their shadows, we learn that the galaxy is richer than we imagined. The sky above us has always looked full of stars. Now we are learning that many of those stars may be surrounded by worlds. Some confirmed, some suspected, some still hidden, and perhaps thousands waiting in data we already have. NASA's TESS telescope was built to find planets, but this discovery shows something even bigger. The telescope does not stop discovering when the observation ends. Its archive keeps speaking. And as scientists develop better tools to listen, the whispers of distant worlds become clearer. The next planet discovery may not begin with a new mission. It may begin with an old light curve, a small shadow, a faint signal, a question asked again. And somewhere in that data, another hidden world waiting to be found.